Hi everyone, welcome to lecture 5.5D. So today is going to be kind of a short lecture. We're going to talk through looking at some sort of harder integrals to do using some supplemental resources. So basically a lot of the times there are hard integrals and someone at some point in history has already figured out how to do them. We have like a big table and there's many of these in books and online. People have spent time compiling these tables. So, you sit down and try to do a bunch of integrals and you write down all your results. So, we've been learning all these techniques, and it's definitely important to be able to do them. If you're, historically, if you're maybe, mid-century, you're doing engineering, you're trying to solve some real physical problems and you just need the answer and you don't really care about the math, this was pretty popular of a tool for people to use to just kind of look up what the integral is going to be and not have to worry too much about solving it. And a lot of common integrals sort of fall under certain templates as well. Like we've seen this one, number 14, right here, several times, where it looks like arctan, and it's always like 1 over something, or 1 over a number times your arctan evaluated at like x over the number. You might start to spot that pattern after you do a bunch of them, to the point where you're like, okay, I've done enough of these, I might as well write down a formula, and then sort of always do them that way. So I definitely wouldn't recommend like relying on these. Like you should be able to know how to do a lot of our ones that we've done so far, but it's kind of just interesting to see them all laid out at once and to know that they exist. So this table will be posted with the lecture. Yeah, so it's just kind of interesting to look for a second. Like we have cosine, sine, tan. Number 5 is nice. Integral tan is one that's not obvious right away, but you do a u sub and it turns out to be log secant, and so there it is. Integral secant also is a little unusual, right? We can do integral secant squared easy because we know the derivative of tangent. We have like this, integral of log x. We've done this by parts problem, where you do by parts and you end up getting this right hand side. We also just have the regular rules, like x to the n turns into this. Some of these, like the early ones, are more like sort of elementary, like definitional, like x to the n, like that's like a building block, and cosine is like a building block. But then, and maybe even tan inverse is like a building block. But then other ones like this log x, it's not like a fundamental one, right? It's like you do integration by parts or something to get there. Yeah, so there's definitely way more on here than we'll ever use in this class, but it's kind of neat to see them all at once. Here, this section is some of these like trig ones that we've been doing lately. This cosine squared one, we saw that you can do that by doing a trig identity. But yeah, it turns out to be this right hand side, so that's can be sort of a shortcut. Some one to point out there is this like sine mx cosine nx. So you could have sine of a number like 2x or 2 theta, and there's like these angle sum identities, and you end up getting this stuff. And these reduction formulas are kind of interesting. Like look, here's sine m cosine to the n, right? This is last lecture we spent a long time figuring out like what the right substitution is. Like we did like u equals cosine or sine depending on the even or odd, and it was kind of a lot of work. But it turns out you can kind of like boil that down into this one formula, which like there's this first part, and the second part has an integral again, but look, the exponents are smaller. So they call this a reduction formula, where I can turn the integral with exponents into an integral with smaller exponents plus some other stuff. That turns out to sort of encapsulate everything we talked about last time if you wanted a single formula. And then here, there's just a lot of like messy looking things. Like there's square roots, stuff that has a squared minus x squared minus a squared. These are basically all versions of like trig inverses and various substitutions and stuff. Like you see some logs, and I think there was a sine inverse here somewhere, right? Yeah, so it's worth just kind of glancing through these a few times. The plan for us is to say, okay, say we had access to this table. Sometimes you still takes a little bit of work to turn your integral into something that can be solved using this table. So for example, this question says, use an integral table to evaluate this thing. So I guarantee you, like, this exact thing is not going to be in the table, right? Like, like this one, this tan inverse one, this x squared plus a squared, like we'd have to identify that our integral like has this a like placeholder in it, right? So we're more kind of looking for the shape. Like, do I see an integral on the right hand side that sort of has a shape that looks like this? So it's 1 over x root 2x minus 9. So let's just maybe keep that in mind. Let's glance through the table, see if there's any integral that looks a little bit like that. You might think like 15 here looks kind of like it, but I think the squared is going to be a big difference. So let's keep looking. So I'm just kind of emulating like how you would actually like use this table if you had a desert island and all this table to work with. Okay, this looks a little promising. There's square roots and stuff. Remember, we're looking for something where like it's 2x, like it's not x squared. The 2 and the 9 are not really going to matter. What's important is that there's an x out front, and then root, probably like a linear thing inside, like an mx plus b inside the root. So yeah, so you can hunt for it if you like, but if you stare long enough, one you might find, I think, is this 88 right here. So here we have, this dx means like there's really a 1 on the top, which is what we have. And we have the x out front, and then we have this ax minus b, right? Our integral, let me write it down, copy it down. Our integral was 2x minus 9 right there. So I think that looks like this one, right? We just have to say what's a and what's b. If we can identify a and b, then we can just copy down this right-hand side, and that's like our answer, right? Okay, well, probably, so the a is in front of the x, so I think a is 2, right? And b is this 9 here. Sometimes you gotta double check the details. Like this here says b greater than 0, so that's true for r9 if 9 is greater than 0. But like if it was 2x plus 9, you'd have to use like this one, I guess, right? It looks similar because it's ax plus b. I told you it was just like a linear thing down there, but this can't be minus 9 according to the rule here, because b is supposed to be greater than 0, and it turns out for some reason it makes a difference to the formula you get. Like these formulas are different, so I don't know where that comes from. I have to think about it for a while, but you see there's little details you have to be careful about. So I think with a is 2 and b is 9, that's our using 88. So we just have to write down our answer. So like this integral, according to the table, is going to be whatever this right hand side is with our a and b plugged in. So it'll be 2 over root 9 is 3, tan inverse, and then a is 2, so root, it's a big root actually, root 2x minus 9 over 9. Apparently, right? So, not maybe the most mathematically interesting, but if you were, like I said before, in the past, a lot of people were like, they had to solve physics problems. Like they're trying to launch rockets or build bridges or whatever. Like, and a lot of times integrals actually just come up, and you just want the answer, and you can plug numbers in, and you want to like know that it's going to work. So, yeah. So it's just worth mentioning that this is also a part of calculus, I think. So let's look at another example. This one here. So yeah, we did this one already. This one says use the table to evaluate this integral. So sometimes you have to do a little bit of work before you even use the table. Here, I promise that if you look on the table, there's not going to be one that's like exactly directly like. Actually, I can't promise that. Maybe there's something weird. It's a pretty big table, but we do know that this like almost looks like it could be like a squared plus x squared or a squared minus x squared kind of thing. And we know, for example, like down here, like look at this guy. This is root of x squared minus a squared. So we don't literally have x squared minus a squared. We have x squared plus 6x. So we're looking at this one. But we do know that we have like some algebra techniques for rearranging the interiors of the integral, and sometimes you can like turn it into something squared minus something squared using a complete the square. So probably this exact formula, root of, like, probably there's no like root x squared plus ax or something inside here. Again, maybe there is. You can check. But even if there is not, if we can transform it algebraically into something that is in the table, we can still use the table. So I want to try to use this 68. So the hard part is we're going to want to turn our x squared plus 6x into x squared minus a squared. So the hint here is complete the square. That's what we got to do. So let's just remember how that works. That's basically just noticing that if I do x plus something squared and end up with 6x plus something, right? This x squared plus 6 is like the first two terms of what I squared something. I squared something. These are terms that can come out. I can ask what number would I have to put next to the x here in order to make 6 show up, and it's 3, because when you FOIL you have 3x plus 3x. But because I have the 3 here, that this term has to be 9 here, because when I FOIL I get 3 times 3. So this is just a little algebra trick where you're like, okay, can I rewrite x squared plus 6x in some way? Well, since it's part of this polynomial that was x plus 3 squared, I can write it as x plus 3 squared minus this 9, right? Just move the 9 over. So that's nice because now we have this, like, you know, if you squint your eyes, this is in the format a squared, or if you squint your eyes, it's in the format a squared minus x squared minus a squared, where like a would be 3 and x, well, maybe x is x plus 3, so we can think about that. But we're hoping to make it look like this 68 down here, right? So let's deal with that, right? I don't want this x plus 3. I just want a single x. And in fact, it's okay if it's a u instead, right? One of the reasons we do a u sub is I'd prefer that to be just a single variable instead of some weird algebra thing like x plus 3. And this is a free u sub because when I do du, it's 1. So it's always free to make a u sub like u equals x plus something or x minus something. So our integral is going to become u squared here minus 9 still, and then just du. Right, it'd be du over 1 maybe, but it's just du. Okay, so now I can identify this as exactly our 68, integral number 68 over here, where like x is u, that's fine, that's just another variable, and a is 3. So according to that, this is going to be equal to u over 2, and it's important that I'm using u here, right? This is a u, so I'm copying that u over here, because like this is going to be the answer in terms of u, but at the end I have to put the x plus 3 back in for it, so I don't want to mix that part up. So here, continuing with u squared minus a squared, that's 9, and then minus 9 over 2 log of u. I'm just copying here. Yeah, and then plus c, I guess. Yeah, so that's the integral in terms of u. And to get a final answer, we'd have to plug everything else back in. So u is x plus 3. So I got to replace all the u's with x plus 3's. Etc. I'm not going to write the rest of it. You have the idea. So sometimes you have to do a little bit of algebra manipulation to turn it into something that's in the table. Complete the square is really common. Like, it might feel a little weird completing the square thing because it sounds a little scary, but like whenever you have something, like it's very, very often a good idea to complete the square if you can, or at least worth trying. So try not to think of this as like a weird algebra, as like a weird thing. Think of it as like a normal thing to try. Okay, so that's pretty much using the table. You have an integral, maybe it matches the table, exactly, maybe it doesn't, but you can rearrange it to match the table, and then you can get an answer. If we were doing like definite integral, you just plug in your numbers at the end, right? Okay, so that's sort of like what the point of a table of integrals is. And like I said, it was kind of more of a tool in the old days before we had so much computers. Nowadays, there's the kind of modern version of the table is basically using symbolic integration, computer integration. So there's a lot of software that has been written. You've probably seen some before. Desmos and Symbolab are kind of versions of this. But there's lots of like fancy research math software, Mathematica, Maple, Sage. There's also like Symbolab and Mathway are more like for education. But basically, instead of having a big table where you have to pattern match and look up in the table, people thought, why don't we just have the computer do that part? And they're right, it's a good idea. You should kind of think of it as a big integration table, right? It's tempting to think of using the computer as like, it'll just give me the answer because it knows math better than me. But it's kind of, I think, better to think of it as like, just like a really big integration table where you have an assistant who does the work of looking it up in the table for you. But it still like has the limitations of a table in some sense, right? Like if there's no like, if it's not like a known integral that people have done before, it's not just going to be in the table somewhere. Now that is for like this kind of software, the kind of traditional computer math software. Nowadays, it's getting even crazier. Okay, so let's see what it looks like to use some integration software to find this integral. So I've got pulled up this integral-calculator.com. I like it. It's a pretty good one. I like that it kind of will show you the steps, which we'll see in a sec. So let's type this integral in. So part of knowing how to do this is to just how to actually type it in. Like you see in this example here, like they're using star for times, right? They're using this caret symbol, this up arrow for exponent. You have to write square root like this, sqrt of x, like this function. And you have to be careful with the parentheses. So you may or may not be familiar with like entering math like this, but it takes a little bit of practice. But let's try to do it for this integral. So it's 1 over root e to the x plus 1. So I think I'll just start with 1 over. Helpfully, it kind of shows what you're writing, so you know if you've typed it in right or not. I have to type square root just like in English like that. It says invalid. It doesn't like that I close the parentheses. That's okay. I bet if I put something in here, then it likes it again. Now I don't want x, I want e to the x, right? So e, you can just type the letter e. I do the caret, which is shift 6, plus e to the x, and then plus 1. So yeah, this one shows you the output, so you know that you've typed it in right. Okay, so let's just see what happens. Sometimes it takes a minute. Okay, so here's our input, and they found this output. There it is. So, who knows how they did it, right? This website does show you some steps. So let's take a look at this. So here's our original problem. They recommended doing a u sub. Okay, so u sub e to the x plus 1. It goes into here, and you get this. Notice we are dividing, when you do this u sub, you divide by e to the x, but e to the x is like u minus 1, right? So that's what this u minus 1 is coming from. They do another substitution, apparently. V is root u, and because you can do this, right? You can do a u sub and then do another u sub. With v is root u, they do dv. You can take the derivative of this. It turns out to be this, du. I think the point of this really is to have u equals v squared, right? When I do that, like this u minus 1 becomes v squared minus 1. And because of the u sub, the root u like cancels, like it goes away. So you just have this guy, which looks maybe a little more familiar, right? Maybe like arctan, maybe, but also you can factor the bottom, and so it looks like they're doing partial fractions. So it's kind of fascinating to see like this is the way they went through it. So yeah, v squared minus 1, you can factor it like this. You do partial fractions. So this is not one step, right? They had to go off on some scratch paper and do partial fractions. Figure out what the coefficients are. You got 1/2 on the top of each of these. Apply linearity, right? You do the integral of each part. Boom. Now these are logs, basically, right? It's going to be like log v minus 1, but it's technically a u sub to do that, right? So they do another substitution. W is v minus 1. Again, that's a free substitution because there's no real derivative of the v. So the dv turns to dw. You get 1 over u, or 1 over w. So it's log w, so log v minus 1. They do the other one, because this was 2 parts, right? They do the other one exactly the same. Plug them in. Now they have to unwind a bunch because they'd made all these substitutions. Here we have we had log w, but that became log of v minus 1, v plus 1. The v, what was v, right? If you're doing this by hand, it'd be kind of annoying, and just scroll back. V was root u, okay. So root u goes into here. What was root u? Well, u, oh, that's nice, they have it here. U was e to the x plus 1, so you get that. And then you're done. So it's kind of a lot. But yeah, so you can imagine like having, it's a lot of steps, but you could imagine maybe messing with this integral for a while and coming up with maybe a similar series of steps. I think the most inspired thing is doing this u sub at the beginning, really. And maybe this second one also, just noticing that you can get to here. Once you're here, you can do partial fractions, and that makes sense. But you're going from here to here is not super obvious, I would say. Something I will mention about this software, that just to be clear, is that like this is not like AI generated at all. This is kind of more old school math software, and there's like these routines and algorithms it has basically for like trying a bunch of common substitutions and then like in a very like rigid step-by-step way, kind of seeing what's going to work. So you could be like 100% on this, basically. There's no like it accidentally just said the wrong thing because it doesn't really know what it's talking about kind of thing. The output kind of looks human readable, like it kind of looks like something the AI spit out, so it's easy to get confused with that. But yeah, there's some other stuff on this page just because while we're here. So yeah, there's some other things you can play with. Yeah, here this blue section, manually compute antiderivative, that means like doing the steps that we just did. Here, antiderivative computed by maxima. So I think that means they're using some more like advanced calculus stuff to get there. They also have like a nice graph. This blue is the original function. This red one is the integral antiderivative we found. So if you need to graph it for some reason, that's sort of interesting. Okay, so yeah, so that's using a math software. There's lots of them. This one's pretty accessible. So yeah, this one might be in the table somewhere if we substitute, but we'd have to play with it just like we did that other example. Something else I want to mention while we're here is computer integration, numerical computer integration. So the example we were just looking at was symbolic computer integration, meaning it does what I said, like it tries a bunch of substitutions, it does like this algorithmic thing to try to actually compute an antiderivative. Some functions, actually, there just is not any simple formula for the antiderivative. So it turns out, for example, this guy, 1 over 2, well, the pi part doesn't really matter, this e to the minus x squared over 2, it turns out that that's just not a function that has an antiderivative. This is not really something we've talked about yet. We kind of sort of assumed that any function you can write down, you can have an antiderivative. But it turns out that's just not true. You can prove, and I think it's a little complicated. I don't know the proof off the top of my head. But it's possible to prove that this function, which the graph looks like this, there's just no antiderivative for it. There's no function you can come up with that when I take the derivative, it ends up being this. No function no elementary function. So there's some details. Elementary function means like built out of normal stuff, like plus, minus, times, roots, powers, sines, cosines, stuff like that. So there's no like elementary function that when you take its derivative you end up getting this. So that's kind of mathematically interesting if you're into that. The 2 here on the bottom doesn't matter. It's really just this e to the minus x squared stuff. This is actually relevant and not just a random curiosity, because you may or may not sort of recognize the shape, but this is a classic bell curve shape. It doesn't look super good in this picture, but if I tweak the various numbers here, like the size of this changes. Like if I make this like a 20, like it's flatter, but if I make it smaller, like for 10 up here, get sharper. So this is like the classic bell curve, like from statistics. So it's used all the time for modeling real life things, population samples and statistical things. So it's not just like a weird math thing. Like people actually need to do this in real life. And actually even more worse perhaps, this integral, like integrating this curve from between two bounds, is actually a super common thing that you want to do when you're doing statistics. You can think of the area under this curve as something to do with how likely it is that certain events happen. If you've ever heard of like p-values or confidence intervals, it's all to do with doing definite integrals with this function. So any statistical study, they have to, maybe the author doesn't literally do it, but their computer does it at some point. They have to do this integral, an integral of this function. They can't do it with an antiderivative, right? There's no, I can't do fundamental theorem of calculus because there's no antiderivative. So how the heck do you do it? Well, you basically just try to do a Riemann sum. You just manually, chop up the area under the curve into a bunch of specific width small rectangles. Just add them up manually like we did in the first week. And then maybe you make the rectangles smaller and see if you get a better estimate. You can't actually make them like infinitely small or whatever because it's a computer and you can't, that's like an abstract math thing. But you can make it smaller and kind of see that maybe you're approaching looks like you're approaching a certain number, and kind of just say that's my estimate for this value of the integral. So that's a big thing too. Also in applied math is using numerical estimates for integrals and things like that. So I think I just wanted to show off one way where you could do that yourself. So this is another common math website, Wolfram Alpha. So it can do these definite integrals. So if I click on this guy here, it gives me a template. I'm not going to type in all the numbers and stuff. I'm just going to do minus x squared. And then let's go from negative 100 to 100. So again, it's not going to be using fundamental theorem of calculus to evaluate this, because the fundamental theorem of calculus was not going to apply to this integral. Instead, we get this number, 1.7. How to get the number? In the background, it did some sort of adding up rectangles thing to get an estimate. This ERF thing, you can look it up if you're curious. It's basically just a name for this function. So it's not really, there's nothing new happening there. Yeah, so here, you get 1.77. We can see what happened if we would do maybe a different range, right? So you apparently also get 1.77. Why is that happening? Well, if you kind of look at this graph here that they're showing, can I enlarge this? Oh. The blue is like the area under the curve. So the curve is going off the top of the page a bit. But like this negative 10 to 10, that's all the way from here to here, right? So whether I do from negative 10 to 10 or negative 100 to 100, I'm still basically capturing all this area in the middle. And so it seems like this blue area in the middle is basically this 1.7, and there's just a tiny contribution to the area from the outside here. So I bet like if I did negative 5, right, because here's negative 5 and 5, I bet if I did that, I would also get the same number. Yeah. Here we can see the graph a little better. But if we get really close, like if I do like -1 to 1, I bet it'll be a smaller number because we're getting an actual smaller chunk of that area. Yeah, so it's like here. So, you know, you can play with this and kind of make some observations and see what you think. But that's definitely something that people do also, I would say, as part of calculus. Okay, so that's numerical integration. Last thing I wanted to talk about today was integral strategies. So we basically kind of talked about this already, but I just kind of wanted to sum it up on one page. So this is not really related to the tables and stuff, but I just wanted to mention it as well. So if you have a random integral that you're trying to do, a question is, what do I even do? How do I even get started? And you know, the main thing to look out for is we have all these techniques we've learned. We learned u-subs, we learned by parts, etc. So it's just a matter of like, what's a good thing to try, like in what order, so you don't waste too much time, right? So I would say that the first number one thing to try is just simplifying using algebra. A lot of people get stuck on an integral that could totally be simplified, but they just didn't quite realize it, right? So like, for example, if I have like, you know, x squared plus x plus x, or plus 1 over x, for example, that looks a little bit scary, but remember, I can simplify, right? I can cancel the x plus 1 over x, and all of a sudden that's the integral I can do, because I can do x squared over 2, I can do x, and then this one's going to be log, right? So, you know, don't forget about your fraction rules. You can split fractions, you can combine fractions, you can cancel. That's like the first thing to try, is to make sure it's in sort of like the simplest looking form before you even try anything else. So that's I would say number one. Try simplifying first. For number two, the next easiest thing is pretty much always u-subs. Very often there's just a simple u-sub you can do, and like the most common way you're going to see that is when, like, I don't know, you have like something inside whose derivative is sitting outside. You have some where part of it is the derivative of another part of it. I notice that this guy's derivative would be 2x. I see an x sitting here. I'm happy because I see that x match. So you know this is going to work. If I do u equals x squared plus 1, du is 2x dx, you're going to get 1/2 root u du. So I'll let you double check that, but it'll work. Another common place where this kind of u-sub comes up is when you have a rational function where the top of it, maybe something like this, right? Here it looks a little scary, but the top is literally the derivative of the bottom. If I do u equals x squared plus x, du is 2x plus 1. That 2x plus 1 is going to cancel when I do my u-sub. In fact, you're just going to get 1 over u here. So if, again, a part of it is the derivative of another part of it, a common case is the top is the derivative of the bottom. Some of our later strategies here have to do with rational functions, where it's a polynomial over a polynomial. So this is kind of covers the case where the polynomial on the top is exactly 1 degree less than the polynomial on the bottom. Often that's a u-sub. Cool. So yeah, simplify using algebra, easy u-sub. I would say those are like maybe the barrier, like the entry level. You know, like that should be first thing, top of your head. Anyone should be able to do that. Look for u-sub. Look for simplification. It's not like tricky until past that point, I would say, right? But this is like, these are like standard. You should always know them. You should always try them. The next tier, I would say, is like, you know, maybe not entry level, maybe journeyman or something. Like you know, do them, learn them to learn maybe, and it's okay if you don't know them all, but you should try to learn them eventually. And then if we get to here, I would classify this as like tricky, and don't feel bad if you don't see it right away. So yeah, for this 3 category, basically there's just several sort of templates that we've seen that work pretty often, and it would be tricky without knowing those templates, but we've seen those templates. So like trig functions, including trig powers. So that's like the sine squared, cosine to the 4 kind of stuff. So we spent a whole lecture looking for that. Basically just, can you identify, is this of that template? Often we have rational functions, so polynomial over polynomial. So I mean something like this one, for example, or something like x squared plus 1 over x plus 1, something like that. Pretty much our techniques to deal with those were partial fractions and long division. So we talked about that in the other lecture, but basically, if you can factor the bottom, you should do partial fractions. And for long division, basically last resort, if partial fractions and u subs don't work. But if the top one is a higher degree than the bottom one, then you can try long division. You can always try long division, but it's just a little bit annoying, so it's good to kind of try the other stuff first. Cool. Then the other one, our template we've seen is products of functions. This is a little bit more generic. Maybe I could lump this up here with the u sub. Maybe that's more standard. But by parts, integration by parts is bread and butter. It's not always easy to identify exactly what the right choices of u and dv are, but there's only so many things to try, and you can just try it and see what happens. Classic integration by parts is something like x times sine of x squared, or not even sine of x squared, just x times sine of x. Classic by parts because it's a product of 2 things. One of them, I know its derivative, so I'm ready to go. I can do by parts there. The one I was drawing before, where I put a squared here, that would be actually a classic u sub, because this x squared's derivative is this x, 2x out front. So small changes can make it look different. Okay, so I would say you ideally would be comfortable like with everything up to here for sure, and then here is more like tricky bonus. Maybe don't expect it on an exam kind of thing. More complex substitution. So maybe something like we saw on that example on the integral calculator earlier, where we had to do like these multiple substitutions in a row. That takes some creativity to find and messing around with it. Sometimes you have to do integration by parts multiple times. You have to keep track of all these different integrals. And we saw last time there's these sometimes just weird algebra tricks, like multiplying by a clever one. That was something like you multiplied the top and bottom by the same thing, and that helped for some reason. Completing the square. Now I know I said earlier you should kind of feel comfortable completing the square, but I'd still put it in this category. Like knowing that you should complete the square in a given integral is not always obvious. But it's not too hard to complete the square, so it's always worth a shot, I would say. Okay, so yeah, I just kind of want to summarize some just like thoughts and strategies, just giving a sense of like what are the things that we've seen. I guess I could add like look at the table onto this list, maybe as a part D right here. Look at the table, because if your integral's tricky enough that none of this stuff has worked so far, then almost certainly it's going to take some sort of weird thing that someone's already figured out, and you can look at the table. Cool. Yeah, so I think that's most of what I want to say about computer integration and integral strategies. So I will see you next time. Thanks for listening.